Okay, in this video, we're gonna start talking about lecture material for test 4, which including the last two modules on the survival guide, module 11, gas laws, and the module 12, bonding and structure. So we're gonna start first subject in gas law, module 11, which is ideal gas. In this module, we're trying to find out some characteristic of gaseous molecules or gaseous chemical substance, which is called the ideal gas law. Now, first of all, what is the difference between ideal gases and gases? Well, typically, when we think about any chemical substance, okay, there are basically three forms. We have solid and liquid and gas, and they're all composed by either atoms or molecules, depends on whether they're elements or compounds. Let's say they have super ultimate particles of molecules or atoms, doesn't really matter. The major difference between solid, liquid, and gas is if this is a one particle, either molecule or atom, let's say molecule, this is one molecule. Now, when you have multiple molecules stacked together in the solid form, this is what they're going to look like. Now, you notice that the way they've been stacked together is in a perfect organized way, and there's zero space between the molecules. So the volume and the size and the shape of the matter is purely determined by the size and shape of the molecules. You just need to multiply by the number of molecules. That's it for that's solid. That gives a solid some basic feature characteristic, which is it has a fixed shape, it has certain volume, it occupies spaces. You can see, you can feel it, you can touch it. Okay, whereas liquid is basically look like this. Now it also has certain volume, which is mainly determined by the volume of each individual particle, and there's nearly no space between the molecules as well. Okay, now which gives the liquid a characteristic that it does occupy the volume, but it hardly have any shape. The shape is mainly depending on the container. Okay, but still the volume is determined. It's only determined by the number of molecules and the individual size of the molecule. Okay, the spaces between distance between the molecules are completely negligible. Okay, whereas in the case of gas, it's a little bit different. Now you may have a molecule of gas here, and the next molecule is probably here, and next molecule is probably here. You see, the spaces occupied by these three gaseous molecules is mainly determined by the distance between the molecules, whereas the actual volume of the particle itself or the molecule itself contributes very little or nothing to the volume or space occupied by the gaseous phase, which usually is much bigger than liquid and solid. So that's the case of gas. Okay, so that gives gases, any gases, chemical substance. Doesn't matter if it's a pure chemical substance or if it's a mixture or if it's a pure element. Okay, gases occupies more spaces than liquid and solid, but it doesn't have any shape. It can hardly have any fixed volume. To be honest, it depends on the container. If you give high pressure or low pressure, the volume will be different. So that's because of the the distance. You can squeeze these two molecules closer if you have a smaller container, or these two molecules will travel as far as they can until they hit the side of the wall of the container. Okay, so it's constantly in motion. Okay, so the point I'm trying to emphasize here is the actual volume of the gaseous molecule here. It seems like contribute very little or nothing at all to the actual volume of this gaseous compound. So here we'd like to introduce the ideal gas. So the ideal gas, the first, or I think it's the more important simplification or idealization than the other one is we completely ignore the size and the shape of the gaseous molecule. So on the PowerPoint, you can see the first item is the volume of gas molecule is 0. So it doesn't really matter if you are a carbon dioxide molecule, or if you're a hydrogen molecule, or oxygen molecule, or you can possibly have different molecules mixed up together. All the molecule itself, okay, should be treated as a mass point, which has a mass, but it does not have any size or shape. So the volume of the gas is only determined by the distance between the molecules. So that's the first condition for ideal gas. The second condition is that since all of the gaseous molecules are constantly in motion, so every collision between the molecules are perfectly elastic, meaning there's no energy lost. For example, if one molecule trying to go this direction and run into this molecule and get bounced back, there's no kinetic energy loss here, meaning the speed of this molecule coming and going back will be exactly the same. Okay, we'll talk about why that is important. Okay, so that's the ideal gas assumption. Now, because of this ideal gas assumption, we can imagine that when you have a gas molecules, it will tend to be more ideal when the temperature is relatively higher and then when the pressure is relatively lower. The reason is because there's no energy lost or gain when you bounce into each other. That means the molecules, they don't really attract or repel each other. That's the reason there's no energy loss when one molecule come in and then bounce back. There's no speed loss here or a kinetic energy loss here. Now, when the temperature is really high, okay, so temperature means the kinetic energy. Kinetic energy is also positively correlated to speed or velocity. So in other words, the faster these molecules travel around, the higher temperature is. So these are positively correlated to each other. In other words, when the temperatures are higher, these molecules are traveling relatively at a higher speed or velocity. When you're traveling at a higher speed, that means even though there might be some loss, it could be completely ignored or neglected. So that's why we say gaseous molecules are more ideal when you relatively higher temperature. At the lower pressure is because at the lower pressure is because when there are lower pressure means there's going to be longer distance or more freedom these molecules can travel inside the container. Okay, so there will be much greater space between the molecules, which make the size and the shape of the molecule itself even less significant. So when we have temperature is high, when we have pressure is low, then we say, okay, this is more closer to the real ideal gas. Okay, so that's the concept of ideal gas.